Good morning, boys and girls, and welcome back. Today we are going to talk about P-series. P-series are series that are, kind of a subset from our integral test because it dates back in Chapter 8 when we talked about functions that looked like our P-series. So here's what a P-series looks like, and then we'll talk about what we talked about before. A P-series is when you have 1 over, n to some power, some p, hence why we call it the p-series. The power might be a squared or a cubed or 1 or, any power, I guess, greater than 1. In this case, this p-series, if I wrote out some terms, would look like this. Again, we're plugging in for the n, and that power stays the same, whatever the power is. If p were to equal 1, I get the series of 1 over n, which would be equal to this friendly series that we've talked a lot about lately, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus, and so on. And this series here has a special name, okay? This series is known as the harmonic series. And like we talked about yesterday when we did the integral test, we know that the harmonic series is going to diverge because the integral from 1 to infinity of 1 over x diverged. And that brought us back to, or this brings us back to that concept now of p-series and when a p-series is going to converge or diverge. But if you remember, we talked about functions like 1 over x squared, 1 over x cubed, as we went from 1 to infinity, and we had some rules kind of set aside. We're basically taking those rules and we're now going to apply them towards p-series. If you remember, back in Chapter 8, we said if you had the function 1 over x to the p, where p was greater than 1, then this was going to converge from 1 to infinity, and it would diverge from 0 to 1, right? And because now with series we're only going from 1 to infinity, we're only moving forward, that's the part we only care about. And so for p-series, a p-series will converge if the p is greater than 1, and it'll diverge if the p is less than or equal to 1. Okay? So again, going back to the harmonic series, because the p is equal to 1, then that one is going to diverge. All right? So a couple of quick little examples here. If I wanted to know if the following, series converged or diverged, the top one, 1 over n cubed, because the power is greater than 1, I know that this is going to converge. And on the bottom one, 1 over n to the 1/2, because the power is less than 1, I know that this series is going to diverge. And again, this could be proven if we go back. I said this is a subset of the integral test. If I go and use the integral test on these, it will show convergence or divergence. I can actually prove it through the integral test. But the p-series test is just a quick test so that I don't have to always use the integral test, just by looking at the powers. All right, so here's another series now. 1 over a times n plus b. Okay, is this going to converge or diverge? I would say first off, in this case, this is not quite a p-series because it's not just an n to a power, right? I've got this a and the b with it. So that resorts me back to I've got to use the integral test to see if this is going to converge or diverge. This is a positive terms, assuming a and b are positive, okay? And it is decreasing as n gets bigger. Those are going to get smaller. So integral test, I have to say positive and decreasing. But because it is positive and decreasing, I can use the integral test and turn this to the integral from 1 to infinity of 1 over ax plus b dx. All right, now I want to integrate this. And so I think to do that, we are going to want to use u substitution. If I make u ax plus b, then du is a dx, or du over a is equal to dx. And then I can rewrite my integral as 1 over a integral of a plus b to infinity. Remember, again, when you do u sub, you need to change your limits in terms of u. So I plugged in 1 for my x to find the limits in terms of u. When I plug in infinity, infinity times a plus b is still just going to go to infinity. Okay, so integral a plus b to infinity of 1 over u du. And now I'm going to go ahead and take the antiderivative of this. And we get 1 over a ln absolute value of u evaluated from a plus b to infinity. And again, I'm going to, again, if you're being lazy, you can continue using infinities. I probably should try to emphasize using the limit notation. So again, I'm going to switch. And in this case, I won't talk about when I switch what I have to do to this anyway. But I'm going to now take this. I'm going to switch to my limit notation so I'm more notationally correct. Normally, in this case, when we switch to limit notation, I would say the limit as b approaches infinity. Since that's on the b side of my limit. However, I've already got b's in this problem, so I don't want to confuse myself. So I'm going to use c instead. Okay, we can always just use any variable. So I took the limit as c approaches infinity of 1 over a ln absolute value from a plus b to c. And now I can go ahead and write this out using fundamental theorem. And now I get the limit as c approaches infinity of 1 over a ln absolute value of c minus 1 over a ln a plus b. And now when I evaluate this as we go to infinity, ln of infinity is infinity. So infinity times 1 over a is still just going to be infinity minus 1 over a ln a plus b. Again, depending what a and b are, this is just going to give me some number, right? When I know what a and b are. So this is infinity minus some number, which is going to go to, then, I guess, infinity. So this is going to diverge. And this diverges, I guess, just like 1 over n, right? So this was very similar to 1 over n starting out with, right? It was 1 over a times n plus b. So the point we're trying to make here, the point I'm trying to kind of show you a little bit, as I guess, it doesn't matter what a and b could have been any number, and it doesn't matter what a and b are. They have no effect on our p-series rule. Technically, we're going to continue to show this on tomorrow's notes. When we start the next day's notes, when we start talking about our comparison tests, and we can actually compare a function like this to 1 over n. But it's good to know that, just kind of a general rule, if you have something in front of your p-series, or if you have a plus something in the back, that is not going to affect your p-series, and it'll converge or diverge just like your normal p-series would. So if this was 1 over an squared plus b, then it would converge just like your 1 over n squared p-series would converge. So we can just kind of sum up what I just said right there. So a and b are going to have no effect on the p-series rule. Okay, you can have a number in front or add a number in the back, and you can still use your p-series rule. All right, here we go. One more again today. The series n equals 2 to infinity of 1 over n ln of n. All those n's, that one's kind of hard to read. Again, this is not quite a p-series, but it's a derivation of a p-series. And again, we're going to get more. We're kind of building and prepping towards our comparison test, since the p-series is so straightforward. If p is bigger than 1, it converges. Smaller than 1, it diverges. We're trying to prepare and get ready for our comparison test a little bit tomorrow. But again, right now, the only tools we have for us is to use the integral test on this. So let's go ahead and do that. First, you're going to at least need to think about, and probably should state, that these are positive terms and they're going to be decreasing. Then we can go ahead and set up our integral. And in this case, again, it looks like we're going to be using a little bit of u sub. So u is ln x, and du then would be 1 over x dx. I know that works out nicely in our integral here. So this becomes the integral ln of 2 to infinity of 1 over u du. And now I'm going to take the antiderivative of that. And we get ln absolute value of u from ln of 2 to infinity. And then again, I'm going to switch and try to get some limit notation in here to be halfway good. So I'm going to get the limit as b approaches infinity of ln of absolute value of u from ln of 2 to b. And then I'm going to use the fundamental theorem. And we get the limit as b approaches infinity of ln of b minus ln of 2. And then if I think about evaluating this limit, we get ln of b as that goes to infinity. This is going to go to infinity minus ln of 2 is, again, is just some number. So infinity minus number, again, is infinity. So this is going to diverge. So it looked like even that ln of n on the bottom didn't affect our 1 over n. This is diverging just like that. And we're going to talk about an easier way to get to this answer tomorrow when we start talking about comparison tests. But know that we can apply a bunch of different tests generally to series. I might be able to apply the p-series or the integral test or the comparison test. And so we're going to start trying to figure out, a big part of the trick again, what is the best test to apply when I'm given a series. Okay, boys and girls, that is all we have for today. Another quickie. I'm going to try, we'll see how this works. I'm going to try to put some videos, a couple extra videos since this is a little bit shorter, on that you can click on at the end of this video on some additional ways to use your calculator when we're dealing with sequence and series. One's like 5 minutes and one's like 3 minutes. Give them a quick watch, I'd say. Learn how to use your calculator with this stuff. Come in with questions. Otherwise, see you later. Have a nice day.